Hello everyone and welcome back to MIE100, the dynamics course at the University of Toronto. This is tutorial 5. We're again going to be working on problems with kinetics of particles, specifically work and energy. And as always, if you have any questions, leave them in the comments below. Alright, so starting with our first problem. A 10 kilogram collar slides on the smooth vertical rod and has a velocity of 2 meters per second in position A, where each spring is stretched by 0.1 meters. Calculate the velocity v2 of the collar as it passes by point B. Alright, so we know the mass of the collar. We also know the velocity at point A. And we know how much the spring is stretched by, so 0.1 meters. We know the stiffness of the spring. And we want to find the velocity at point B. So the first thing we're going to do is we're going to try to find x2. So if we look at our spring over here, we know that the length here is 0.3 meters, and we know that this length over here is 0.4 meters. So this length, let's call it L2, is going to be equal to 0.3 squared plus 0.4 squared under the square root. That's just Pythagoras. It's going to give us 0.5 meters. And now we want to find the unstretched length of the spring, so it's going to be L naught is equal to 0.4 minus x1. This is the unstretched length of the spring, because we don't know that yet from the question. And we know our x1, so our L naught is going to be equal to 0.3 meters. Now, we want to know what's the extra length that's been stretched in the position of point B. So we've got x2 is equal to L2 minus L naught. L2 here is the stretched spring length. And here it's just the stretched part. So we know what our L2 and our L naught is, so 0.5 minus 0.3. That's going to give us 0.2 meters. Now that we have our x2, we can now use our work energy equations. So work is equal to the sum of the kinetic energy plus the sum of potential energy. And we know that our work done is going to be equal to 0. And this is because there's no external forces acting on the system. So there's no external force, so the work done has to be equal to 0. The only forces acting on the system are gravitational, elastic, and non-working constraints. Therefore, we know that T1 plus V1 is equal to T2 plus V2. Or, in other words, delta T plus delta Vg plus delta Ve is going to be equal to 0. Now we just plug in our known equations. So for kinetic energy, it's going to be half m v2 squared minus v1 squared. And for the gravitational energy, it's going to be mg h2 minus h1. And for the elastic potential energy, it's going to be 2 half k x2 squared minus x1 squared. This is because we have two springs acting on the system. And all of that is going to be equal to 0. Now we're going to plug in our known values. Here H2 is equal to 0. This is going to be equal to minus 0.3 plus 800, 0.2 squared minus 0.1 squared is equal to 0. And that's going to give us a final answer of 2.26 meters per second. And now for our second problem, the collar has a mass of 2 kilograms and is attached to the light spring, which has a stiffness of 30 newtons per meter and an unstretched length of 1.5 meters. Collar is released from rest at A and slides up the smooth rod under the action of the constant 50 Newton force. So there's an external force this time. Now we want to know what the potential energy of the spring is at time is equal to 0. And we want to know the velocity of the collar as it passes by position B. And we also want to draw a free body diagram of the collar when it is in position B. Okay. So the first thing we know is the mass of the collar, the stiffness of the springs, the unstretched length, the external force acting on it, and we know that at VA it's 0 meters per second. Now for our part A, we want to know the potential energy at point A. First things first, the gravitational potential energy is going to be equal to mgh, but at point A we're going to say that h is equal to 0, so Fg is equal to 0. And now we're going to calculate the stretched length of the spring, so XA is going to be equal to LA minus L naught, and that's 2 minus 1.5, giving us a stretched length of 0.5 meters. And now we can calculate the elastic potential energy, which is half kxa squared. We plug in all our known values to give us 3.75 joules. And since the gravitational energy is 0, so the total potential energy is going to be equal to 3.75 joules. Okay. Now for part B, we want to know the velocity at point B. So we're going to use our work energy equation. So work is going to be equal to the sum of kinetic energy and the sum of potential energy. Kinetic energy is going to be equal to half VB squared minus VA squared. We know that VA is equal to 0. So that gives us half mVB squared. Our potential energy is going to be equal to VEB plus VGB. These are the potential energies at point B. And it's going to be minus the potential energy at A, which we already know. So we're going to plug in our potential energy equations. And to do that, to find our known values and to find xb, we're going to draw our little spring. We know that this length over here is 1.5 meters from the diagram, and this length is 2 meters. So that means our LB is going to be equal to 1.5 squared plus 2 squared all under the square root, giving us 2.5 meters, and from that we can calculate the stretched length xb. That's going to give us 1 meter. Now that we've got all our values, we can plug it into our potential energy equation. To give us sum of potential energy equal to 40.68 joules. Now we're going to use the work equation, which is sum of U is equal to F multiplied by S. Excuse me. That's going to be equals to, F is going to be equal to HB minus HA cosine 30. And we're just going to plug in our known values because we know this is equal to 0. And we're going to get work done equals to 64.95 joules. Now we're going to go back to this equation over here and plug in our known values. So that the only thing we're looking for is VB. Now we can easily calculate our velocity at point B, which is equal to 4.93 meters per second. And now for part C of our problem, we want to find the free body diagram at B. We just want to draw the free body diagram. We don't necessarily need to know the magnitudes. So this is our collar over here. This is going to be the mass, the gravity acting on the collar. This is going to be the external force, F. And we know that the spring is going to be acting this way, which is equal to the spring constant times S. And the normal force is going to be pointing this way. And now for our last problem. We've got a system released from rest with the spring initially stretched 25 millimeters. We want to calculate the velocity v of the 60 kilogram cart after it has moved 100 millimeters down the incline. We want to also determine the maximum distance d traveled by the cart before it stops momentarily. And we're going to neglect the mass and friction of the pulleys and wheels. Alright, so for this question, we know that the spring constant is 300 newtons per meter. We know that the mass is 60 kilograms. And first of all, at t is equal to 0, we know that v1 is 0 meters per second, and we also know that x1 is equal to 25 millimeters. And then part 2, at d2 is equal to 100 millimeters when it starts moving down the incline. We want to find out the velocity at that point. And then part 3, at v3 is equal to 0 again when it stops momentarily, we want to find the total distance traveled. So we've got two things to worry about. The first thing we're going to focus on is from step 1 to step 2. So we're going to use our work energy equations. U is equal to sum of T plus sum of V. There's no external force, so our work done is 0. And we know our kinetic energy and potential energy equations, so half mv2 squared minus v1 squared plus half k x2 squared minus x1 squared minus mg h2 minus h1. And here I'm making it negative because it's going down. You can make it positive and then switch those two, but it's however you prefer. We know that our v1 is equal to 0, and we know our h1 is also equal to 0. To find our h2, we have our distance d2, and we know the angle, which is 20 degrees, so we can easily find our h2, which is equal to d2 sine 20, giving us 0.0342 meters. And now for our pulley system, we've got a constrained motion system happening here. So this is all, we'll call this distance S. And we have 3 S's, so our 3 S's are going to be equal to a constant C, which is the length of the cable, which means that the additional stretch of the spring, so however much the spring is going to stretch, that extra part, has to be 3 times the additional distance by the cart. So let me write that down. The additional stretch in the spring runs at 3 times the additional distance by the cart, because of this relationship over here. And that means that our 3d2 plus x1 is going to be equals to our x2. Now we know our d2, which is 0.1, and we also know our x1. So x2 becomes equal to 0.325 meters. And then we're going to plug in our known values into this equation. So half multiplied by 60 multiplied by v2 squared plus half multiplied by 300 multiplied by x2 squared minus x1 squared, then minus 60 multiplied by the gravity, and 0.0342. All of that is going to be equal to 0. So we can easily find our v2, which gives us a velocity of 0.382 meters per second. Now we're gonna start analyzing our system from 1 to 3. And we're gonna use our work energy equations again. We know that the work done is equal to 0, and we also know that kinetic energy is equal to 0 because our V1 and V3 are equal to 0. It starts from rest and then it stops momentarily at 3. So sum of kinetic energy has to be equal to 0. So all we're left with is our potential energy, which is half kx3 squared minus x1 squared minus mg h3 minus h1. And we know our relationship here is going to be the same. The stretched length is going to be equal to 3 multiplied by d3 plus x1. And here we're going to plug in our known values. So 0, we're going to plug in our known values into this equation. So 0 is equal to half 300, and then we're going to substitute our x3 with this expression here. So 3d3 plus 0.025 squared minus minus 0.025 squared minus 60 multiplied by 9.81 multiplied by d3 sine 20. And then when we simplify this equation, it gives us 1,350 d3 squared minus 178 d3 plus 0.9367 is all equal to 0. So we're going to use our quadratic equations to make d3 the subject, which is minus b plus minus b squared minus 4ac over 2a. This is our a term, b term, c term. That's going to give us a final answer of d3, which is equal to 0.1325 meters. That's the end of our problem. And this was the end of our tutorial. Thank you so much for watching. I hope you found it helpful. As always, if you have any questions or concerns, you can always email me at noor.doidar@mail.tutorano.ca, or you can leave your questions in the comment section below. Thank you and see you next week.